Hello. Hello, can we start? Dr. Santosh, can we start?
Just a minute. Please hold for 1 minute. I will check whether the YouTube live stream is on or not.
Okay, good.
Okay, we are. Ma'am, kindly start the session.
Okay. That's good. It's exact time. So, good afternoon, everyone. I'm Benita Fertial, Secretary of the Association of Quaternary Researchers, AOQR. It's Monday afternoon, and we are here again with yet another very interesting talk, which will be delivered by Dr. Waliur Rahaman from the National Center of Polar and Ocean Research, Goa. So before we begin, I would like to please request all the participants to please, mute their audio as well as their video also, because it is a lot of distraction to the organizers and the person who's speaking. So it's an earnest request. Please do that. Secondly, so we start. So on behalf of our president, Dr. Vandana Prasad, our office bearers, our founder members, our honorary members, our ECR team, and on my own, I welcome you all to the AOQR ECR webinar series. This is the second talk. Last week, same time, we were hearing our first speaker, Dr. Amzad Hussain Laskar. I'm very happy to share the feedback of that talk. So we had about 500 quaternary researchers watching that talk live and through Google Meet and the YouTube platform. And you will be happy to know that in 6 days, we have 1K views of that talk in the YouTube link. So that's really wonderful. We also received feedback forms from 349 participants, and thank you thank you to all of those who sent us the feedback forms. We need feedback from all of you because we want to improve and organize this webinar better. Out of the 49 feedback forms that we got, 24.5 rated us excellent, and 74.7 they rated us good and very good. And of course, we could not satisfy 0.8% of the people. That's 3 out of 349. But we'll try to make it like 100% excellent. We also had participants from other countries like Brazil, Pakistan, Philippines, Israel, who sent us the feedbacks. So it was really, really good to hear that. So even after this talk, after Dr. Waliur Rahaman would do his talk, we'll send you a feedback link. I think in the WhatsApp group it's already sent. So please fill it and send it back to us. We also request you to please become members of this association, and there was some misunderstanding regarding the fee because we had kept a one-time admission fee and then the annual fee. So the first time you need to send both. And I thank all those people who became members in the last week, and a group from NIO was there. I thank you all. And this help would be this this monetary the funds that we really needed to develop a website and other things and plan our other meetings, virtual meetings, and that we have in the agenda. There were some suggestions on the technical glitches also. I want to point out here that as we have a number of participants, and we know that Google Meet has a restriction of 250 people. So we just shared that link with the faculty and the students we were giving the YouTube link. So kindly bear with us. It's not a fault. We all wanted
Hello, ma'am. Are you there? Hello, ma'am. Are you there?
Ma'am, please
I'm so
start.
sorry.
Yeah, you are
Can you hear me?
disconnected. Yeah,
I'm
now
so
it's now
sorry.
it's clear. Now it's clear. It's okay. Thank you.
Yeah,
Please
now it's
continue.
clear. I'm so
Please
sorry
continue.
about this. I just lost the connection. So
Please.
I was saying that we've got a very good feedback, and I'm very thankful to all of you who've become members. So before we dive into the talk of today, it's my privilege to introduce the young speaker to this new quaternary family. Born in January 1981, Dr. Waliur Rahaman did his master's in 2004 in applied geology from Aligarh Muslim University, India. Dr. Waliur Rahman started his research career at Physical Research Laboratory PRL Ahmedabad as a junior research fellow, and for his PhD thesis in the field of isotope geochemistry. His PhD and postdoctoral work at PRL Ahmedabad during 2005 to 2011 was very well recognized by the global scientific community. Based on his research, he was awarded the Alexander von Humboldt Fellowship by the Humboldt Foundation, Germany, in 2013. Dr. Rahman joined NCPOR Goa in January 2012 as Scientist C. Since then, he has been working in the field of paleoclimatology based on the Antarctic ice course, paleoceanography, and isotope geochemistry. After joining NCPOR, he also established a new metal-free clean laboratory. It's known as IsoTrace, and it's equipped with the state-of-the-art instruments in the field of isotope geochemistry, such as the multi-collector ICMS. Then they have the ICPMS for the analysis of trace elements, radiogenic and stable isotopes. With these additions of these new analytical facility and laboratory, the IsoTrace laboratory at NCPOR has become one of the well-reputed isotope geochemistry lab, not only in India but also in abroad. Currently, he's heading the isotope geochemistry section at there, and he also extends support to many PhD students and young researchers from the other Indian institutes and universities for the measurement of radiogenic isotopes and interpreting results. So currently, his group has been actively involved in the cutting-edge research in the field of non-traditional stable isotope and their application in paleoceanography. So Dr. Rahman was also awarded the Certificate of Merit by the Ministry of Earth Sciences, Government of India, last year, that is 2019. And as stated before, in 2011, he got the very prestigious Alexander von Humboldt postdoctoral fellowship by the Humboldt Foundation, Germany. With this brief introduction, I invite Waliur to deliver his talk on the ocean acidification threats under high CO2 world, a lesson from the past record of ocean pH. Over to you, Waliur. And I request again everybody, please switch off their video screens while the speaker is speaking to you. Thank you. Over to you, Waliur. Uh, your mic is mute. Please unmute. Hello?
Yes, okay.
Please.
Now?
Yeah,
Yeah.
it's okay now.
Please
It's
share
okay.
your
Okay.
screen.
Yes,
Yeah.
yes. Okay. So thank you, Benita, for your kind words of introduction and giving me the opportunity to speak on this great forum that you have been actively involved. So, okay. So coming to the directly to my presentation. Okay. Yes. 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 It's. Can you see the slides? First slides.
No, not yet.
Okay. Just a minute. Slides. It's okay now.
Yeah, it's okay now. You can make a full screen.
Yes. 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 Okay. So, okay. As I'm told that I will be allowed to speak for another 40 minutes and 20 minutes for questioning. Means you can ask questions. Okay, I don't know 20 minutes will be sufficient or not, but I will try as much as, and then rest you can send me an email. And I have this email is there in my first slide, Waliur at the rate of ncpor.res.in. Okay, so basically, I'm a geochemist and I work on various scientific problems related to ocean, atmosphere, Antarctica, Arctic. But I have chosen this particular topic, the ocean acidification and its threats, because what I thought that okay, this is a probably it's a larger audience, so I can cover large audience. At the same time, many actually do not know about this threats. So in high CO2 scenario, we often talk about climate change, global warming, sea level rise, but many of us actually do not know what is ocean acidification and its threats in already it's going on, but in higher CO2 means in the coming decades or end of the century, you will see much higher threats. And many of us, though we know, but we don't recognize that there is a threat. Okay, so coming straight away to the topic, okay. So what do we mean by ocean acidification? So we have started releasing a lot of CO2 by fossil fuel burning and other activities. And since industrial era started, so say that is 1815, and then we have already put a lot of CO2 to the atmosphere. And if you see the CO2 level, pre-industrial CO2, that was 280 ppm, and now we have already crossed 400 ppm, so more than almost 120 ppm, and that is creation by us. Means we have actually released this much of CO2, and we are responsible for this increase of 120 ppm CO2 to our atmosphere. And as a result, there is a reaction. So you know the ocean and atmosphere is basically it's a coupled system. So as a result, you see CO2 when it's come in contact with the seawater, it's from carbonic acid, and it's again get dissociated and then from it's a hydrogen ion and bicarbonate ion. So if you put more CO2 into the atmosphere, basically you are increasing the partial pressure of CO2. Then basically you are producing more of your reaction is shifted more towards the right. So basically you are producing more hydrogen ion. And we know that hydrogen ion means basically it's a more of acid. So we know the standard definition of the pH, that is minus log of hydrogen ion concentration. So more of a hydrogen ion is a less pH. And this process is called ocean acidification. It's occurring within ocean. So this is what we call it ocean acidification. And this has a direct threat to some of the living organisms. And those are basically calcifiers. So their body cells made of calcium carbonate. So either they are not efficiently formed their cells or their cells started dissolving. So this is a direct threat to those calcifiers. Now just to give a scale, means how the pH scale is, and just to give you idea, though it's a textbook class 7, class 8 textbook, probably you will get the pH and its definition. So you see the pH scale here, pH, the neutral pH is actually 7. And on the left side, if you go, so it's pH is reduction, so more of a acidic. If you see, for example, coffee, tea, milk, and tomato, lemon juice, so basically it's acidic of a 2 to 3 or 4 pH. If it is higher pH, more than 7, for example, the human blood, baking soda, and then some soap, bleach, so these are higher pH. So basically, it's a more of an alkaline. Then you see the pH, sea outer pH is actually 8.2, the average global pH, and pH is minus log of hydrogen ion concentration. So any slight change in the pH, if you see, pH basically it's in a log scale. So if you reduce by 0.1 unit, that has a huge change in the hydrogen ion concentration because it's in a log scale. For example, here if you see from 8.2 to 8.1, this change in hydrogen ion concentration is almost 26%. If you reduce by zero point 0.3 unit, let's say 8.2 to 7.9, the increase in the hydrogen ion concentration almost 100%. So if you change slight change in the pH, then it's a huge change in the hydrogen ion concentration. But now in the ocean, how much these things are changing, this pH, and how fast it's changing. If you see, we have a nice record of instrumental records of ocean pH as well as the CO2. So there are two stations that quite well-known station, time series station, which is basically measuring different oceanic as well as atmospheric parameters. The stations are in the Pacific, one is Aloha, another is the BATS. And then in the Pacific, if you see the Mauna Loa, so observatory, which is continuously measuring the CO2 concentration in our atmosphere. So we have a nice record since 1960. Then we have a CO2, seawater PCO2 record, that is, and then also we have also started measuring pH since 1989. So we have a nice record of ocean pH as well as atmospheric CO2, ocean CO2 since last 3 or 4 decades. Now, if you see the ocean, so we have a model observation. So as I talked about that instrumental records of ocean pH, at the same time we can also model ocean pH for the future CO2 scenario. So in a model, they frequently talk about that RCP2 or RCP 8.5. These are the scenario basically. So at different CO2 level. So RCP basically represents a representative concentration pathways. So at 2.6, which project for CO2 for this century. At the end of the century, if you see the 2.6 scenario, so it will reach 400 ppm. But in other extreme scenario, if you see RCP 8.5, which is the extreme scenario, at the end of the century, it will reach almost more than 900 ppm. And correspondingly, we have also the pH, model pH for the ocean, different ocean, Arctic, Southern Ocean, tropics. And you can see here that ocean pH, before it's the 1900 it started somewhere, average pH is 8.2 and then started declining. And the end of the 21st century, you can see pH will get reduced to 7.6. So it's a huge change. And if you see the special map here, actually it's a surface pH of last in the next decades up to 2090. You can see that different parts of the ocean and then the pH change is almost 0.5 unit, and the northern ocean, basically Arctic, is going to be affected more because you can see the pH change is huge in case of Arctic. Southern Ocean is also another reason where we can see the large change. And there are studies that says that whatever the CO2 we have already pumped into the atmosphere, out of 30% that anthropogenic CO2 is already taken up by the Southern Ocean. So Southern Ocean, in a way, it's a big sink of atmospheric CO2. Now, just to give you a comparison, so if you see the special CO2 pH map, so before industrial era, so it's 1850, and then the model projection at the end of the century, 21st century, you can see there is a change, huge change, and these regions are basically Arctic, and then coastal upwelling zones are going to be affected more. So most of the pH change at the end of the century, you can see these regions. So coastal upwelling regions as well as in the Arctic Ocean or the Southern Ocean. Now, this pH change has a direct impact, and it's a threat to the our ecosystem, that marine ecosystem, and it has also direct impact to our socioeconomy because many resources actually comes from the ocean, and for example, fish, oyster, and many of the things that are coming from the actual our coastal zone, so coastal ocean. And this CO2 or ocean acidification impact is not only happening in isolation, so it is part of the large system, so it has a feedback mechanism to the larger climate system. So it will give a feedback to also future climate change. So these are the direct actually threat or the impact to our system. Now coming, see the coastline. We have a huge coastline. We have almost 7,500 kilometer large coastline, and along this coastline, across this, we have also extended exclusive economic zone from where we get a lot of the marine resources, including fish and other things. And almost 30% of the total populations actually getting resources from these coastal regions. So it's economically, these particular regions are providing a lot of support to our people. And then India is it's the seventh largest actually marine fishing nation in the world. Now coming to the CO2 or its impact in terms of ocean acidification, if you see in terms of the CO2 production, so country-wise you can see here. So among the large contributor, if you see the China, India, China, United States, European Union, India contribute very less as compared to the other countries. In terms of per capita, if you see, we are contributing much lesser compared to the other nations. So in a way, actually, we are contributing. We are contributing least, but we are suffering most. So who are the people, those or the organizations or international bodies who are actually involved in this research, ocean acidification? There are a few organizations that pretty well known in this research. Let's say NCPOR, NOAA, then UK Ocean Acidification Group, SOLAS, and then IAEA, International Atomic Energy Agency. These are the larger actually scientific bodies who are directly involved in this research. And based on the publications, though this compilation is long back, I got it, but it's based on that compilation, we can see that in terms of research publication in this particular aspect is very less from India. So we, as a research, in terms of the research in India on ocean acidification, we are much lagging behind. So we need to do more on this research because we are actually affecting a lot. So before, so what I just gave you a glimpse that whatever I talked, that basically I talked about much recent time scale, means last few decades or last 200 years or like that after the industrial era. But just I will take you back in time, much longer time scale. So just I want to give you the perspective of the past ocean or the CO2. How was that when there was no human? So it's a million years back, almost 200 or 300 million years ago. When so not only so that time all the CO2 was much higher, and once upon a time this millennia time scale CO2 was much higher than what we were experiencing. We have now 400 ppm. Back in time, geological time scale, we have our Earth atmosphere experience much higher than that. Almost sometimes it shoots up to 1000 ppm. So, and that most of the CO2, if you see the major CO2 source, that is actually volcanism. So when there is an extensive massive eruption, so there is a large emission of atmospheric CO2, and that also shoots up our CO2 level in our atmosphere. So one such scenario, one study that was published in Science a couple of years ago, they found that the Permian Triassic mass extinction is actually linked to the ocean acidification. So there are many mass extinction events happened in the past. So one of such extinction is Permian Triassic mass extinction. So this is somewhere here. so 250 million years back. That time CO2 reached much higher level near 1000 ppm, and then correspondingly ocean pH was reduced to 7.6. So it's a quite large change or reduction in terms of the pH. So it's almost 0.5 or 0.6 unit reduction. And so because of this acidification or lowering of the ocean pH, most of the ocean biota got extinct. So this particular mass extinction event actually linked to the ocean acidification during this Permian Triassic period, which actually happened due to this extensive volcanism. Now I am coming a little recent as compared to what I just taught. So it's a quaternary glacier interglacier period, which is, let's say, less than a millennia. So if you see, we have a record, nice ice core records, CO2 records of last 800,000 years. And if you see the CO2 fluctuation here in the red curve, so that varies from 180 to 300 ppm. So the variability is almost 120 ppm. So it's never exceed 300 ppm. And correspondingly, CO2 ocean pH was varying from 8.1 to 8.2, not much. So it's a quite stable CO2 and then ocean pH. And then after 1850, we can see that in 2017 we reached the CO2 almost 400 ppm and correspondingly reduction in 0.1 pH, so it's 8.1. And then the model prediction we have just, I showed you in my previous slides, that CO2 reached up to 800 ppm and then pH reduction up to 7.1. So now let us see the two scenario, model scenario, pre-industrial and the industrial. In the industrial scenario, at the end of the century, the model simulation. So now with this background, so now there are few key questions before us. So the first question that raised, the why atmospheric CO2 is actually rising almost uniform. So any part of the place, anywhere you measure atmospheric CO2, you will get the CO2 concentration almost equal, but we can see that ocean pH is not uniform. It's actually varying from a lot from one to another place. So why different parts of the ocean responding differently to the atmospheric CO2 increasing almost uniformly? And then we can see that what is the internal variability of the ocean pH in different part of the global ocean. We do not know. So what is that internal variability? And then the third question is the relative contribution of the natural. So ocean has its own internal variability and then anthropogenic CO2 forcing. So whatever the pH change we are seeing or we are observing in the records, and that is basically it's a sum of two factors. One is the natural, which is due to the ocean internal variability. So ocean has its internal mechanism of processes which is contributing to this change, and another is the CO2. So we need to know actually what is the relative contribution from the ocean, so which is basically its internal variability, and which is coming from the anthropogenic CO2 rise. And third is this model projection or the simulation that we are getting, basically, it has a lot of uncertainty. So we should know that how accurate these predictions are for the ocean acidification trend and its impact in a future scenario. Okay, so coming to that, so our approach was mostly model based, which I just talked about. So, and that has an uncertainty. Model always has an uncertainty. So this was a one approach. But now I'm going to talk about another approach by which you can also get back in time that what was the pH, and then you can get the trend, and probably if you can also predict what is going to be the scenario in a future CO2 scenario and its corresponding pH. And for that, as a paleoceanographer, we can reconstruct based on the proxy records. And then for that we need the archive, suitable archive. And here we have a nice archive like Foraminifera, but Foraminifera it works in much longer time scale, kilo-year time scale. But another archive that is basically corals, and corals has a nice actually annual band. So individual bands actually represent individual year. So you can resolve the individual year, so which is almost comparable to instrumental records. And then proxy people use for ocean pH reconstruction, that is alkaline trace element ratio, as well as boron isotopes. And among them, boron isotopes are found to be pretty more robust and reliable. And we have also adopted this method or the technique of proxies, boron isotope. Yes. So, but before getting into our study, I just want to give you a glimpse of how actually this proxy works in our system, and then how we can employ boron isotope as a proxy for ocean pH reconstruction. So, boron in ocean basically it exists as a borate and boric acid, and with the abundance of boric acid 80% and 20%, and then boron has two isotopes, boron 11 and boron 10, and it's a stable isotope. So with the abundance 80%, 11 and 20%, 10, like that. But one thing here you remember that this ionic species distribution in the seawater, that is very much critically dependent on the pH. So if ocean pH somewhere 8.1 or 8.2, and it has a distribution of this or this. Now if it changes the ocean pH little bit, then it will also, the ionic species distribution will also be changed. And if you change that distribution, then there will be isotope fractionation, which we measure, and we express this isotope fractionation in terms of change in the oceanic pH. So there is a direct empirical relation. So this is pH, and then on the right side you have all the equilibrium constant, or the dissociation constant, boron isotopes. So if you compute the boron isotope measured in your archive, and you know the dissociation constant, then you can directly calculate that how much pH is. So this is how it's work. Now coming to the record, if you see that based on the boron isotope records in corals, there are not much, but probably 9 or 10, latest probably total 10 records are published, but most of the records are actually from the either Pacific or Atlantic. So within the Pacific, the records are from the South China Sea, and a few are from the Great Barrier Reef, and few are from the Atlantic. But you see here, there is no records from the Indian Ocean. So we actually do not know how Indian Ocean actually responding with the rise of the atmospheric CO2. So in other words, we do not know what is the ocean acidification trend in the Indian Ocean. Now coming to the records that we have, so I have just compiled all the records, boron isotope records, you can see, and then boron isotope is actually, it's a linearly proportional to the pH change. So pH, so it's a it's a linear relation with the pH. So here you can see there is a, based on this parametric, this lowest field basically, we can see there is a steady decline in the pH and much more sharp decline here after 1950. Though there is a large scatter, but based on this fit, we can see there is a clear-cut shift or decline trend. Now, the sector-wise, different oceanic sector within the Pacific, you can see the Great Barrier. It's a lot of variability in South China Sea, you can see, and then Atlantic. And this red line we have calculated based on the theoretical calculation. So within this time, how much CO2 change, and correspondingly, how much pH we should expect. So based on the theoretical calculation, we have calculated this red curve. Actually, this is only CO2 driven pH change in the ocean, and that change, if you see the red curve, is very very less as compared to the variability in the actual ocean record, means actual boron isotope record. If you see here, so so it means that if you see it's a more than 90% variability. Actually, it's contributed by the ocean own processes. It's not by the CO2 or atmospheric or anthropogenic CO2. So almost less than 5% or 5% probably it's contributed by the anthropogenic CO2, because you can see there is a little bit of say decline trend. So most of the contribution is actually coming from the oceanic processes itself, not the atmospheric CO2 increase. But one thing you should remember here, this increase is pretty consistent, and consistently it's decline with respect to CO2 rise. Okay, so now coming to our Indian Ocean. This is, please remember, this is we're going to give the first record of ocean pH for last 30 years, or 26 years to be precise, for the Indian Ocean, based on the boron isotopes in corals. And these coral samples were collected from the Lakshadweep region, and then we measured boron isotopes. So first thing we did, we cut across the growth axis, we did the chronology, and that it somewhere it's 2013 to 1990 basically. So this is the time span it represents. So these are the works that we carried out in our lab, and this is our lab at NCPOR Goa. So we have a nice metal-free clean lab where we do all kind of this isotope geochemistry, and this is exclusively for the boron chemistry. And one of my PhD student, Tariq, basically he's doing his PhD work on boron isotopes. And boron isotopes, so we from the samples to finally boron isotope measurements, it's a lot of work, and it's a quite tedious work. And there are different methods, and we have adapted this particular method to extract the pure form of boron. So basically we did the sublimation after cleaning and all, and then we got the pure form of boron, and finally we measured boron isotope using this state of the instrument, which we call MCICPMS. It's a multi-collector inductively coupled plasma mass spectrometer, which is now, since last 3 years, we are actually routinely measuring various isotopes, mostly the radiogenic, and then few stable metal isotopes like boron and silicon. And these are my students, they are working and measuring the isotopes. So coming to the results, so here, this is our boron isotope records. You can see here, it's a lot of variability here. And now you can see in our record, boron isotope records, and we have converted into this pH scale, this side on the right, you can see. So with this is our actually sample interval, this started in our interval, somewhere 88 to 2014. So with this time, there is a rise of atmospheric CO2 almost 50 ppm. And you can calculate that how much actually pH is actually already changed, corresponding to 50 ppm rise in atmospheric CO2. Then, so we are expecting in our record that we also should expect this kind of a steady decline. But here, interestingly, we can see here, our record does not show any steady decline trend. Rather, there we can see there is a huge variability, a large fluctuation here. And if you see here, we have compared these pH records. Surprisingly, it is matching with the ENSO records. So ENSO, basically one of the parameter, that is the SST index, mean of 3.4. We have compared our pH records with the ENSO record, and we can see there is a nice correspondence between the pH excursion in the profile with the ENSO. So ENSO, I am not going to talk much about the ENSO. Many of you already know. And then ENSO, basically it has a two phases. One is El Nino and La Nina. El Nino, basically El Nino scenario, there is a SST, positive SST anomaly in the Eastern Pacific. and it influence also Indian Ocean. So when there is a El Nino, we can see less rainfall over India or Australia. So and then also there is a not only atmosphere, we have also seen that there is a effect in the oceanic processes. So we can see this thermal anomaly, which positive SST anomaly here over the Indian Ocean, and just opposite we can see in the La Nina conditions. So this our study, particularly the Western Indian Ocean, Arabian Sea, which is also influenced by this El Nino or La Nina. Basically, we commonly call it ENSO. And how they are actually influencing, I will explain in my subsequent slides. But to summarize here, we can what we observe in our records, there is a large variability of ocean pH in the Arabian Sea, but we don't see there is a steady any decline trend corresponding to CO2 rise. And this fluctuation that in our pH record is very much actually driven by the ENSO-driven oceanographic processes. What are those processes actually getting influenced by ENSO? I will explain in the next slides. But to confirm that, okay, this ENSO oscillation is there in our record or not, we have just done this statistical analysis. It's nothing but it's a power spectrum analysis. So we can see there is a significant periodicity, almost 8 years. And then we have done the cross wavelet. So wavelet basically that will decompose your time series into frequency and time domain. So we have done the cross wavelet, and cross wavelet actually highlight the common highest power in these two time series. So in the Nino 3.4 and then boron isotope records, we can see there is a the common highest power at this window, at this band. So it confirms that there is an influence of ENSO in our boron isotope records. Okay, so what are the factors? So you know that ocean pH is influenced by or modulated by oceanographic processes that could be physical, biological, or I would say it's a biochemical. So physical, it's a upwelling, mixing, or even temperature change in temperature or salinity that could influence your ocean pH. And another, the biological productivity. So chlorophyll, for example. So when there is a more productivity, it will consume the CO2 from the system. So you will see the change in the ocean pH accordingly. So basically, in this physical or biological processes that can influence, so which are actually the oceanic processes that can modulate the ocean pH. So here in the Indian Ocean, we know that there is a certain wind and current systems that operates in the Indian Ocean, and also another processes which is quite well known in the Arabian Sea or in the coastal region of Indian Ocean. So and the Arabian Sea, you see, that is upwelling. So upwelling, this actually causes a lot of productivity. This upwelling supplies a lot of nutrients to surface, and that also led to a lot of productivity in the Arabian Sea. So this process, these processes, physical driven biochemical processes, quite common in these part of the ocean. But these processes are also modulated by this the large daily connection with the Pacific, this ENSO, La Nina, and El Nino. So here, upwelling is one of the processes I would just like to mention here or stress upon on this particular thing. So if you see, this is a major data along the section here in the Indian Ocean. The ocean pH, if you see the vertical distribution of the ocean pH, and if there is an upwelling, strong upwellings, you can see that the bottom water is actually it's a lower pH, but whereas in the surface, near the surface, you can see the pH is much high. So if you have more upwelling here, it means you will bring less pH water to the surface. So by simply mixing up two water mass by upwelling, you can change the surface ocean pH. So these are the physical processes which can actually influence the ocean pH. So coming to with this schematic, I will demonstrate how actually happened during this El Nino and La Nina conditions. So basically here you can see during El Nino condition we can see higher pH, and in La Nina condition it's a lower pH. So during El Nino we have seen that El Nino condition, basically El Nino condition that suppress the upwelling. So we see the less upwelling during the El Nino condition. So as a result, this surface water flow comes up, but it's very less. So we expect the higher pH here. But on the reverse condition, which is the La Nina, we can see there is a intense upwelling, and due to this intense upwelling, the surface, this deep water, means below the 250 meters or 400 meters, the low pH water that comes up to the surface, and that can reduce the pH. So by changing the strength of the upwelling, you can simply change the surface ocean pH, which is actually we are observing in the El Nino and La Nina conditions. So this large variability actually explained by these El Nino or the ENSO events. Now to extend these things, so there are also independent studies that suggest that during in a future decades or century, in a warming scenario, we expect more frequency and amplitude of these ENSO events. And this is not my study. This is basically it's based on a model or some observation. There are many studies that suggest that the warming scenario, they are going to be more of a ENSO events, and the amplitude of those events also going to be more. So, and in our study, what we have observed, there is a relationship between these ENSO events and pH. So, combining these two, we can suggest that in a future warming scenario, the pH variability is going to be high. In other words, the extremes of the ocean pH is going to be more. So, increase in the pH extremes Indian Ocean, this is going to be very, very crucial for many of the calcifier, particularly these marine organisms, not only the calcifier, but also in other organisms, in terms of their adaptability, their resiliency, because you know the extreme condition nobody likes. No species, even we don't like the extreme condition. When there will be more cold events or more warm events, we feel uncomfortable. Similarly, in the ocean, if there is a change in the ocean pH, in the extreme sides, more pH or very less pH, which is not going to be good for this kind of an organism, particularly calcifiers. So to summarize my talk, so we are going to give the first pH record from the Indian Ocean for last 30 years based on the boron isotopes of coral, and our record shows large variability and mostly driven by the oceanographic factors. We don't see any anthropogenic CO2 driven ocean acidification trend. So it's even that is there, but it is masked by your large internal variability driven by oceanographic ocean internal processes. And this pH variability in Lakshadweep region primarily modulated by ENSO driven upwelling strength, and in the extreme pH or the pH extremes may likely to increase in the Arabian Sea, which may be crucial for adaptability and resiliency of corals and other calcifiers. That's all. Okay, thank you very much for your patience. So if you have any questions, you can ask me. And acknowledgement. So basically, most of the work carried out by one of my PhD students, Tariq, and they are my collaborators who are also actively involved in this particular work. Thank you.
Thank you, Waliur, for the very interesting talk. Can you hear me? Yeah.
Yes.
So, I think we had a number of participants who are still there and who have been watching you and listening to this interesting talk. We have 3 questions in the chat box. If you could just see, Waliur, and there is a question with Swapnil Nawal.
Yes. Yes, yes. I
Kumar
can
and
see.
Prayanta Gupta. So can you please answer them? You can read
This
them
is
and answer
the
them.
questions. Let me read. Yes, yes.
At the last, just scroll down.
Uh,
Yeah. So you start
yes,
from
it's okay. I'm starting
Swapnil
from the
Mapat.
last. Okay, okay. The last question is,
Okay. But
yeah.
then if
So
you
last
want to,
question is Dr. Rajesh Agnihatri. Okay, I would like to know how ocean acidification may affect sulfur biogeochemistry of coastal water. Okay, sulfur, but yeah. So if you change the weathering pattern, so sulfur mostly for the ocean is coming through the weathering, or probably anthropogenic sulfur. But anthropogenic sulfur, I don't know that how much is actually going to affect, like CO2 is going to affect. But in terms of pH, I don't see it's going to affect much, because sulfur emission probably is not that in terms of anthropogenic sulfur, how much it has increased with time due to anthropogenic emission, I don't know, but definitely in terms of it's lesser than CO2. So it may affect, but I don't know the sulfur dioxide and corresponding to ocean pH, how is good. I don't have an idea in terms of the CO2 and atmospheric CO2, how much sulfur dioxide actually gone up, and how, I mean, here you are referring to anthropogenic sulfur. If it is, so I don't have much idea, but definitely not like CO2. CO2 we have changed a lot from 280 ppm to 400 ppm, but that much increase I don't expect in sulfur. But another possibility is through sulfuric acid weathering. So if through, or maybe some effluents discharge from the industry, and that is going to affect localized, but not in a large scale that I talked about. Yes. Then another.
okay. There are many questions now. So I think it was, yeah. Now whether you want to
Yes.
start from the bottom
Uh,
again.
so, okay. Another question is, okay. Excellent talk. It is. My question is: can acidification balanced or reduced? My question: can the acidification balanced or reduced? Okay. So probably means. Okay, so far we have seen the projection for the CO2. It is. I don't think it's going to stop unless this kind of a pandemic happens. But even it happens, so I don't think we're going to reduce the CO2 level. So since in the last 6 months, maybe constant, but it is still 400 ppm. It's persistently there, the CO2 level. So yeah, it's a unidirectional change, but unless some another feedback mechanism, I don't know, but this is not going to happen in this time scale, shorter time scale. So the in this time scale we are changing CO2 a lot, but counter mechanism to balance it, I don't think is going to happen in this time scale. So it's going to be unidirectional. So I am not going to see the either steady state balance or going to stop. So yeah, with the rise of atmospheric CO2, another century maybe going to continuously increase. So it's a monotonic curve, monotonic increasing curve, CO2, or corresponding decreasing in ocean pH. Okay, so another question is how much time left for this, Vinita? How much time left? Another, hello, can you hear me, Benita? Yes. Can ocean acidification change the morphology or aquatic fauna? Yes, it can change. For example, corals. So if there is and these corals are much more vulnerable to this ocean acidification. So yes, that morphology corals is one of the living example probably. So many of the corals species and it's known like Australian coral reefs, they are under severe threats, and many of the coral reefs are already died because of this ocean acidification. Not only ocean acidification, also thermal stress. It's a combined. So yes, definitely the morphology is going to change. And then in terms of also morphology of individual species, probably like foraminifera cells or maybe other any tiny species, maybe their cells are going to be size maybe going to be lesser. Probably I don't have idea, but yeah, some maybe they can try to adapt, and in order to adapting the higher pH, probably they can their morphology they are going to change. So yes, they can change. Yes, any. Yes, okay. So any there are a lot of questions, and probably time will not permit to answer. But if you can send those questions to my email, waliur@ncpor.voice.in, then I can. But if I get thousands of questions, I will not. But some of the genuine nice question, I will try to answer, and I will send my reply through email.
Okay. Value, that sounds good, I think, because yeah, we have very good, interesting questions, and there are many now. So I feel we can send you all these questions. We'll just copy them, send it to you, and then we can share it with our viewers in their emails, or we'll find a way to share it with them. So I feel it was a nice talk. Then we should end because it's just 2-3 more minutes, and Dr. Manoj MC is waiting to deliver the vote of thanks. I request him to please do this honor.
Thank you, ma'am. Thank you very much. A very good evening to everyone. It gives me an immense pleasure to deliver the vote of thanks for this webinar to all the dignitaries and researchers joining here. I would like to thank Dr. Waliur Rahaman for accepting our invitation to give the second AOQR webinar series. It is a very interesting talk, and which is very visible through the responses from the researchers and the other faculties from the YouTube and Google Meet platform. I am very sure all of us got many information and ideas from this interesting talk. So let me express my sincere thanks to Dr. Waliur Rahaman for this wonderful lecture. Thank you, Dr. Waliur Rahaman.
Thank you for your patience, and thank you, Vinita, giving me the opportunity.
Oh, thank you, AOQR.
Thank you.
Last gathering. Probably first time I am addressed to this so
Yeah, this is a big platform, and I feel our platform should be bigger, because coordinator research is so diverse, and it's so vast, and we have so many academic institutions working on it. I think we need a single platform. We needed a single platform so that we could share our ideas and make it interdisciplinary. So yes, Manoj, you want to continue?
Yes, I want to continue. I also thank actually all the people who made this webinar a success. And I want to thank the director, BSIP, and the president of AOQR, Dr. Vandana Prasad, vice president, Dr. Pradeep Srivastava, secretary, Dr. Vinita Pathya, treasurer, Dr. Sandosha, and all founder members of AOQR for their continuous support and encouragement. Also, a special thanks to Dr. Vinita Pathya for always being there to give ideas and make all our effort a successful one. I would like to express my gratitude to our AOQR honorary members, Professor Ashok Singhvi, Professor Vishwas Khale, Professor Hema Chitan, and Professor Chamnial for guiding us and showing us the right path for our improvement. I also wish to express my sincere thanks to Dr. Sendil Kumar Sadasivam, who is behind this designing and of all our webinar flyers, abstracts, and also the ordinary Chronicle newsletter. I also wish to thank all my other ECR colleagues for their continuous support. And thank you for Dr. Jyoti Srivastava and Dr. Trina for moderating the questions as well. Like our first AOQR webinar talk, this time also we got immense response from many scientists, researchers, and students. I thank all the dignitaries, professors, teachers, researchers, students, and all the quaternary researchers for joining. This program is successful only because of your interest and cooperation. I also express my sincere gratitude to BSIP IT team, especially to Mr. Kathiar and Dr. Nilay, and also again to Dr. Santosh for their making the webinar successful. Please fill the feedback form, which is already provided. This will help us to improve the upcoming talk and other initiatives. Now we will wait for the next interesting talk on 21st September. Thank you everyone.
Okay, thank you. So we close this talk and we meet next Monday at 2:30 p.m. Thank you. Namaskar. Bye. Thank you, everybody. Thanks.